The moon had been photographed by a variety of spacecraft. Machines had landed on the moon to observe it. Now it was time for man to make ready to go there. I'm Larry Ross, Director of Space Programs at NASA's Lewis Research Center in Cleveland, Ohio, and I'm your host for the 6th episode of our 13 programs called Journey Through the Solar System. Now let's see parts of several NASA films which document both the science and the excitement of this Apollo lunar program.
I know my own impression is that it's a vast, lonely, forbidding type existence or expanse of nothing. It looks rather like clouds and clouds of pumice stone. And it certainly would not appear to be a very inviting place to live or work.
Scientific sextant observations made on Apollo 8 were a practical, potentially vital gathering of scientific data. Taking the longer view of the scientific value of the mission, comment was made by Dr. Leo Goldberg, astronomer.
I believe the Apollo 8 mission will ultimately prove to be of enormous scientific importance as a vital step that had to be taken before men actually land on the moon. Once they do, the exploration of the moon is bound to give us crucial information on how the moon and other bodies in the solar system were formed.
Doctor in a second, I hope. Roger. Map and we're there. Got 2 crates. Roger. You saw the docket, Charlie. Good, master alarm. Everything looks snug.
Apollo 10 had a rugged flight plan. It combined the features of the 9 flights before it and was a full dress rehearsal for the infinitely complicated lunar landing to follow. Astronauts Stafford, Young, and Cernan became the second group of 3 to see this sight. And they were the first with the potential to see it from a point 60 miles closer than it appears in this scene. It was a prime objective of Apollo 10 to duplicate the Apollo 11 flight plan in every way: the timing, spacecraft performance, the performance of men and equipment on Earth. As they disappeared behind the moon for the 11th time, they were still together. When they next appeared, they were 50 feet apart, flying formation. John Young radioed his companions below. "You'll never know how big this thing gets when there ain't nobody in here but one guy." And they answered, "You'll never know how small it looks when you're as far as we are." Here in the lunar environment, as Apollo 9 had done in Earth's environment, the crew was able to check out the lunar module's landing radar, navigation, and guidance systems. They were also proving out the descent rocket, an engine which can be throttled like an ordinary car. reflection in the window comes from the astronaut's sleeves as he took the pictures.
Down among us, Charlie. Roger, you're weaving your way up the freeway.
The waterless sea of tranquility was their target, and the descent orbit swept them in lower and lower for the first pass over landing site number 2. This is a preview of what the crew of the Apollo 11 will see when they head in for lunar landing.
Down 2.5. Forward. Forward. That's 40 feet down, 2.5. Picking up some dust. 4 forward. 4 forward. Drifting to the right a little. That's okay. Contact light. Okay, engine stop. We copy you down, Eagle. Tranquility Base here. The Eagle has landed.
Through the window of the Eagle, Armstrong and Aldrin see what no human eyes have ever seen before. Their spacecraft casts a long shadow across the undisturbed dust of centuries. The first footsteps on this strange new world must be taken cautiously. The moon has only 1/6 the gravity of Earth. The nature of its surface was still unknown.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
In addition to collecting rock and soil samples, the explorers leave behind a seismometer. This highly sensitive device would send back valuable information on external meteoroid impacts, as well as internal lunar movements. A 100 prism laser reflector would help man to measure the exact distance from Earth to Moon to an accuracy of 6 inches. These were the first of many experiments which will be taken to the Moon to provide man continuing and increasing knowledge about the Moon and the vastness of space beyond.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engines running. Commit. Liftoff.
Apollo 12 lifted off in the driving rain.
Pete Conrad reports that your program is in. Tower clear.
Conrad climbed out first.
Okay, I'm at the porch. Hey, I'll tell you what we're parked next to. What? We're about 25 feet in front of the surveyor crater.
They prepared an experiments package to be left on the moon, an automated scientific station called ALSEP that would send information to Earth for a year, powered by a nuclear electric generator. ALSEP, an acronym for Apollo Lunar Surface Experiments Package. Piece by piece, they assembled the station.
Okay. I've got the solar wind deployed here.
The solar wind experiment, to measure atomic particles thrown off by the sun as they strike the moon. A device to measure the moon's tenuous atmosphere. A magnetometer to measure the lunar magnetic field, which would later be found to be 10 to 20 times stronger than many scientists had expected. A seismometer to measure physical properties of the crust and interior. and the data station to collect the experimental measurements and transmit them to Earth. With ALSEP deployed, Conrad and Bean began collecting geological samples.
Look out, there's just a rock. Look at that. Son of a gun. They gotta have that. 15 at 1. -1. -1. 6% fuel. 10 feet, -1. 8 feet, -1. Contact. Man. Okay, Houston, the Falcon is on the plane at Hadley. Roger, roger, Falcon. No denying that, we had contact. Houston, the Hadley base here. Tell those geologists in the back room to get ready, because we've really got something for them.
Scott and Irwin were located on an undulating plain situated between the Apennines and Hadley Rill, an area selected by the scientists as being one of the most geologically significant sites on the moon. They would observe the layering of the lunar terrain, most clearly seen in the formation 14 miles to the south, called Silver Spur. This layering, later to be observed in the mountains and the rill, gives scientists a direct look at the structure of the moon and a deeper insight as to the significance of the collected samples. 60 miles above the moon, Al Warden orbited in the command module Endeavour, operating experiments, his observations adding to the wealth of scientific data already accumulated.
Okay, I'm looking right down on Letro now, and a very interesting thing. It looks like a whole field of small cinder cones down there.
The detection of cinder cones, clearly of volcanic origin, helped solve another element of the controversy about how much of the moon was formed by volcanoes and how much by meteoroid impact. Warden was operating a series of experiments in the scientific instrument module. These included a mapping camera to shoot lunar features and simultaneously the star field for accurate location of these features, a panoramic camera, a laser altimeter for accurate topographical mapping, and a series of experiments to analyze the chemical makeup of the lunar crust. In the estimation of a number of scientists, this orbital research station would provide the most important information collected during the mission.
Look at that. Almost see twinning in there. Guess what we just found? I think we found what we came for. Crystal and rock, huh? Yes, sir. You better believe it.
To the untrained eye, it looked like just another rock, but its large crystals, formed in pairs called twinning, showed it to be a section of primal lunar crust, formed during the earliest history of the solar system.
Yes, it is. If we could just get our shoulder under that. Okay.
Their first stop was at the drill they had left during the second EVA. This core tube was the deepest sample ever collected from the moon, perhaps the deepest we would ever get, 8.5 feet beneath the surface, cutting through 58 distinct layers. This would not only tell us more about the lunar structure, but contained in this soil were traces of particles emitted by the sun billions of years ago, which would give us a clue to the early years of the solar system.
Young set up an ultraviolet camera to provide the first astronomical observations from the moon. He took pictures of the Earth's upper atmosphere and magnetosphere and their interaction with the solar wind. He also photographed the interstellar gas present throughout space and the ultraviolet halos that appear around galaxies. Young placed a series of sensors in the soil, then fired explosive charges, mapping the lunar subsurface much as geologists on Earth use explosives to search for oil.
4, 3, 2, 1, fire.
Young used a portable instrument to measure the local magnetic field. He would later record the most intense magnetic field ever found on the moon, far higher than scientists ever suspected. With Duke acting as photographer and Young as driver. They put the rover through a full test.
Man, you are really bouncing.
Then, one of the most spectacular discoveries of the mission.
Look at the size of that biggie. It is a biggie, isn't it? It may be further away than we think. No, it's not very far. It was just right beyond you.
And we better press on for the big boulder.
Okay, we're headed that way. You get the tongs, John? Yep. I'll carry the rake.
That big black dot.
Fantastic.
Like right here.
If we could see to the bottom, we could say for sure if this big black rock is right out of the bottom. But my guess from the old photographs is it probably is.
Okay, that sounds like a good guess.
Pottery, it's obviously very cohesive because it's the bottom of the core is not smooth, it's very jaggedy and fragmental-like.
They would sample several locations on this EVA, but none would cause more excitement than the find at the crater called Shorty.
Oh, hey! There is orange soil. Well, don't move it till I see it. It's all over. Orange! Don't move it till I see it. I've stirred it up with my feet. Hey, it is! I can see it from here. It's orange.
That's the volcanic mix.
Somebody unplugged silver.
Fantastic, sports fans. It's trench time. Jack, that is really orange.
I think it's the most exciting we have come across since the beginning of the Apollo program. I believe that it's going to be the most rewarding of all the finds on Apollo.
99, proceeded, 3, 2, 1, ignition. Right away, Houston. Bets are good.
17 was the last Apollo mission to the moon. Now, what did we learn after the data, rocks, lunar soil, and photographs were returned? A NASA film called The Moon, an Emerging Planet begins to tell us the results.
In many respects, our moon is one of the strangest bodies in the entire solar system. Of all the terrestrial or four innermost planets, only Earth has such a large moon. Compared with the terrestrial planets, the moon's density is much lower than we might have expected. Compared with Earth, the chemistry is much different. Before the Apollo program, three major theories arose to dominate scientists' thinking about how the moon was formed. One suggests that the moon split off from the Earth and was flung into orbit around our planet. A second theory suggests that the moon originated as a twin planet, perhaps from materials left over from the formation of the Earth. The third theory holds that the moon was captured by the Earth's gravitational attraction, having been formed somewhere else in the solar system. There are problems with each theory. It has been suggested that it would be easier to explain our moon's absence than its presence. Nevertheless, from the data returned by the remarkable Apollo flights, as well as unmanned missions, we have learned a great deal about the moon's evolution and early history. It has become, in a sense, an emerging planet. Unless it split off from another planet, it must have originated as a tiny body, perhaps one something like Phobos, one of the moons of the planet Mars. And it grew by a process of accretion, an accumulation of objects drawn together, often in massive collisions by gravitational attraction. These objects ranged from microscopic dust particles to asteroids. By 4.6 billion years ago, the moon had reached its present dimensions. During the last 10 to 100,000 years of this primeval bombardment, the collisions may have generated so much heat that the entire outer shell of the moon may have turned into a seething global ocean of molten silicate materials. Once bombardment slowed, the liquid shell began to cool, solidifying over a period of tens of millions of years. Crystals rich in calcium and aluminum formed. They rose to the surface and produced a mush which eventually solidified to become the dominant light-colored material we call the highlands. Simultaneously, dense crystals rich in magnesium and iron formed and sank to the bottom, becoming a distinct dense layer. There was now a lunar crust, a product of millions of years of crystallization. 100 to 300 million years later, radioactive heating became extensive enough to melt materials in the shell just beneath the crust. The melting produced pockets of liquid, giving rise to volcanic eruptions 4.4 to 4.3 billion years ago. At the same time, it seems that globules of molten material rich in metallic iron may have accumulated, and they settled down into the center to form a core. If 2 to 3% of the original moon consisted of metallic iron, the core could have a radius about 1/5 that of the whole globe. Such a differentiated moon, with a crust, a mantle, and a core, came as quite a surprise to many scientists who had expected the moon to be homogeneous, with materials distributed more or less evenly throughout. A molten core rich in iron could have functioned as a huge dynamo, much like the Earth's core, and produced a magnetic field. This would explain the magnetic properties of many of the lunar rocks which have been returned by Apollo crews. According to theoretical studies, the moon and Earth serve as very efficient celestial vacuum cleaners, and within less than 100 million years after their formation, they should have swept up most objects in their vicinity. Surprisingly, 600 million years after the formation, or 1/2 billion years later than we would have expected, huge objects were still impacting on the moon, helping produce the rugged surface. Some of them were as large as the state of Rhode Island. The final ones blasted out the great circular basins we see on the moon's face today. One of the final large impacts, which we call the Imbrium event, produced the circular feature which now serves as the right eye of the man in the moon. By the time of the Imbrium impact, the exterior of the moon had cooled to depths well below the crust. The interior, by contrast, began to warm up, a result of natural radioactivity. At a depth of 150 miles, perhaps 300 miles, a zone began to melt, producing liquid silicate material that accumulated in pockets. The liquids then found their way to the surface, sometimes following fractures in the crust, sometimes forcing a passage through solid layers. One volcanic flow after another filled in the great basins produced by the large meteoroid impacts, and became what Galileo Galilei called the lunar maria, or seas. After some 1.5 billion years, major volcanic activity on the moon had come to an end. Except for a last gasp of volcanic activity originating deep in the lunar interior, rare meteoroid impacts, such as the one which produced the crater Copernicus, and occasional small moonquakes. The peace of the moon has been largely undisturbed for 3,000 million years. We have thus learned a great deal about those early events and processes which produced the moon. And it seems likely that similar events and processes were at work on our own planet. The Earth's early geologic records, however, have been largely obscured by extensive volcanic activity, faulting, folding, erosion, sedimentation, and other geologic processes. What few of the ancient records we do still have on Earth are being illuminated by our lunar studies. It is clear that the moon had a violent and dynamic early history, and that major geologic activity had come to an end by 3 billion years ago. Unlike the moon, the Earth did not die. Indeed, its geologic activity increased. By a half billion years ago, hard-shelled animals had appeared on Earth, and they left their fossils in rocks we find today. It was only about 200 million years ago that the present continent split and began to drift apart, a process which continues to this day. In essence, it is possible that the Earth and Moon had quite similar early histories. In studying the Moon, we are taking our first close-up look through what has been called a window to the history of our solar system.
The moon has shown no evidence of life. Still, we wondered if there was life elsewhere than Earth in our solar system. The next logical candidate for the search was Mars, fourth planet from the Sun. During our next episode, we will examine Mars from space. This is Larry Ross saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio.